Hello, everyone. Welcome to the meeting for March 14th, 2024. This is the general meeting for the Data Science at Georgia Tech CLE 2024 group. And this meeting is focused around our baseline submissions and modeling. So the first two presentations have been about kind of the overview of the labs. We've had a little bit of discussion around the data, some data exploration, downloading the data. So this meeting is about modeling. How do we learn patterns from data? And it's also a little bit about making those first submissions. So here's a outline of our today's meeting. We'll go through a little introduction. We'll do the milestone presentations. We'll talk about what's happening next meeting, and then we'll have time for questions and discussion. So the introduction is just a little bit about modeling. So again, modeling is taking the data sets that you might get from all the different competitions and to build a program that is able to learn patterns from that data. We might learn a linear model that's able to map independent variables to dependent variables. We might learn some neural network to see really complex nonlinear relationships between variables. But what we're doing is we're building a program to learn from data. And this usually involves building a pipeline. You might have a stage that is cleaning a bunch of data to set it up for another stage where we're splitting up the data into a test set, a validation set, a training set, and to finally build a model that learns from the data. These pipelines are ubiquitous through the data science community, so it's usually a good idea to have them and to have a process that you can use to build models that is sustainable. And the last thing I wanted to mention is a baseline is useful to have. So baseline is a result that you can have a fair comparison with all your models. So for example, you might build a really simple baseline that is just the mean of all your data. If you're making some sort of regression, or maybe it's randomly choosing a class if you have a classification problem, or choosing a single class. But a baseline lets you know whether you're making progression towards a goal of making a good model. And this is usually facilitated by the competition-focused aspect of CLE. So the leaderboard exists, and you'll be able to see yourself moving up the leaderboard. So that's just kind of a brief overview of modeling. So I think today we'll see a little bit about different approaches to all the different problems that we have in this group. So let's get into the team updates. So for bioasq, I'll ask Wenshin to take over.
Okay. So the bioasq competition is about biomedical semantic indexing and question answering. The first task we have is the test 12B for semantic question answering. The setting for this lab is, given a biomedical question, we need to return the relevant articles from the PubMed database, as well as exact and ideal answers to the question. We're building two systems to solve this problem. The first system is a two-level information retrieval system. So we first extract keywords from the medical questions currently we're thinking about using LM or a spacey name entity recognition model. We are comparing the performance of the two. And then we will use the keywords to extract queries to the PubMed engine. After getting a smaller set of the relevant articles from the engine, we will further do a ranking algorithm to find the most relevant snippets. So the millions records to 1,000 records is done by PubMed search. This is the first level retrieval, and then the second level retrieval, we are thinking about parsing the documents in the sentence level and then run sentence transformer to embed those documents and then rank the documents by the distance in the vector space. And at the end, we'll get the top 10 articles and snippets for the question. And then the next slide. The second system is for question answering. So this will be built based on in-context learning using a pre-trained large language model. Here we're thinking about constructing prompts using the question and also attach a context to it. The context will be constructed using the snippets that we generated from the first system. And then we will also attach a few examples in the prompt. Currently, we are manually compose those examples using the question answer pairs in the training data sets. After we get, we'll send a prompt to LLM, and after we get the response from LLM, we will do some post-processing for the exact answers to satisfy the format of the competition. So that's it for bioasq 12b. And then the second task we have is called bioasq. This task is to recognize 8 types of nested named entities in Russian and English PubMed article abstracts. So currently we are only focusing on English abstracts. So the 8 types of entities include the ones I shown on this table. So some medical terms, anatomy, those are just medical terms, and then chemicals, device, disorders, findings, injuries, lab procedures, and physiology term, I think. Next. So for the modeling part, we will, the input is the abstract, a piece of text, and then we will run LLM model on each type of entity to extract those types to extract the entities from the text. So the prompt of the LLM will also consist of examples of an article and its golden entities. We plan to experiment with different LLMs to evaluate the performance. And after getting the response from LLM, which is a list of entities, we will do further filtering and aggregation on those entities using this tool, using this system called Unified Medical Language System, which is a tool that does indexing and classification for medical terminologies and concepts. The reason that we want to build some rules around the UMLS is that the bioMNE datasets is actually composed using some of the rules they built around the UMLS, and I think those can get us more accurate results if we do the processing based on the same type of rule. And also the other reason for this is that our model uses the general purpose LLM, and the entity that we want to recognize in this task are very similar, the entity types. So sometimes the LLM will just confuse this with different types, so we want to further classify them using our own algorithm. In the picture below, we have an example. So the article. So here is an article about the mild cognitive impairment. And we want to recognize the disordered entities in this text. So for the prompt, we construct to send to our, and we will attach an example, which is another abstract. It's about a seizure, some seizure study, and in this text we have a disorder entity list, which is the golden list, and we send this to LM. The LM will return us the entity it recognized in the article that we want to investigate. And in this list, it actually has mixing, although we ask for disorder entity type, but it returns a lot of entities which doesn't belong, and one of them doesn't belong to the disease, the disorder type. So for example, the last one is actually a lab procedure. So we think that our UMLS rules that we will compose will be able to identify this case. Yes, so that's it for bioasq.
Excellent. Thank you, Wenshin. Now for IDPP, I'd like to have Ritesh present.
All right. Thanks, Anthony. You guys can hear me fine?
Yeah.
Okay, perfect. Yeah, IDPP, just reminding everyone from the last time, that's intelligent disease progression prediction. So we're basically predicting how the disease is going to progress. And in this case, we are trying to predict a neurological neurodegenerative disease called ALS. It's so our target, our job is to, given sensor data for X number of patients, we're supposed to predict what their score is going to be. And this score is usually used to see how the patient's disease is progressing, getting better or worse in either direction. So it's pretty important for prognosis, pretty important for clinical trials overall. So yeah, it's up till now, the way the score is being given is by a questionnaire that's given to the patient, and patient gives a score about himself on each of the metrics for a score from 0 to 4 for 12 questions, and a total sum was made out of it, and that's the score. So this is very subjective because it depends on patient to patient. What these guys want to do is try to see if we can get sensor data from patients and use that to predict the score, so it becomes more of an objective way of getting to the score rather than being very subjective. So that's just a little quick background. If you want to move to the next slide, Anthony. So here we didn't have the data last time. So during the last presentation, so I just quickly put together one slide just to show how the data is there. This data is a panel data set, which is not very uncommon, but it's not very common either. So I just quickly gave at the top a panel view of how the data set is usually structured. So we have like X number of patients. Here we have 4 person. And for each person, we would have some timestamps of the sensor data taken at whatever times over here. Ideally, you would want the times to be matched between all the patients. But in real life, that usually is not possible. So that's what we see in our data set as well, that the times that we are given the sensor data for each and every patient is not identical. They are all over the place. But this is how the data set is structured. It's not just one person, one score. It's one person, 5 scores. Another person could be 3 scores. Another person should be 15 scores. Could be anywhere. There is no fixed length. It's a variable length sequences. Each of these patient data is basically called one sequence, and it could be of variable lengths. So that is how the panel data set is usually structured. A quick information about the data set. On the left-hand side, we have only 52 patients data. So downloading the data was not a problem. I hear all the other teams saying it took 10 hours to download the data and 15 hours to download the data. Our data got downloaded in 30 seconds. So just one good thing about it. But anyways, so we have only 52 patients data. It's a very small data set. So that has a huge amount of its own challenges. Models become overfitting very fast because it's hardly anything there. So anyway, that's one of our targets, one of our issues. And we have variable number of targets as well for each patient, as I was mentioning before. We also don't have to predict just one score. There are 12 questions, as I mentioned in the beginning. We have to predict the score for each 12 of the questions independently, not like a collective sum of them. So there are 12 outputs, 12 target outputs in this prediction question. And looking to the data, we had a lot of missing sensor data. So although the data set was small to begin with, on top of that, we have a lot of data missing. So we have to, in some way, interpolate them or scratch them. There are multiple data processing steps that we are going through in different directions, trying to see which one is going to be most helpful. I put a small diagram of target distribution. As you can see at the bottom, the x-axis is basically the scores, and 48 is the maximum. So you can see that most of the distribution kind of lies about 30 or 35. So anything lower than 30, 35 is very underrepresented in the entire data set. So smaller data set with a lot of scores underrepresented poses its own challenge, because then the model doesn't get enough chance to learn. And then it ends up making incorrect predictions for the underrepresented classes. So that's one challenge. And on the right-hand side diagram, I'm just showing the number of target scores available for all the patients. So we have all the patients down here, about 52 of them. Some of the patients, we have 7 target scores, some of them 6, and all the way down to only 2 target scores for a lot of them. Right? So it's variable. So yeah, those are some of the challenges. So some of the modeling techniques that we gave a quick try on to get some kind of a baseline understanding is random forest, KNN, and LSTM is still under debug. I don't think I have implemented it very right, so I'm still trying to implement it correctly. But at least random forest and KNN give us about 4 to 5 root mean squared error on the collapse data. Like we collapse everything just to one line and just try to predict it and see how close we can get. And this prediction is made on the collective sum, not on individual questions yet. I'm just trying to do on a collective sum yet. So that's where it's like a top line understanding of where we are standing. We're still trying to create our pipeline. As Anthony mentioned, we would like to create a pipeline, but we're still trying to see how we're going to split our training and test set data, because again, being only 52 patients is very tricky to kind of give too much to the test set, but then we obviously have to give something to the test set. So yeah, so that's what from the EDA quick undergoing of EDA. You want to go to the next slide, Anthony? Shashank, you want to go over this slide?
Yeah. So the first thing that we made was to create a straightforward baseline. So looking at the EDA, we figured out that a lot of the scores were pretty static. They would change every once in a while, and then they would remain same for a while before changing again. And so the simplest thing that we decided to make for the baseline was the last observed carry forward model, which was able to give us an RMSE of 0.63. This is a per question RMSE, which is basically predicting for each question. And what we noticed, like while we were doing modeling, as Ritesh already mentioned, is that the data would overfit really fast as soon as we added one more feature other than the previous score. It's basically using it to understand the nooks and crannies and simply overfit to the training set. The training error goes down really fast, and consequently the test error goes up really fast. So we basically needed more data, or in some way. So our task one is to predict the clinician's assigned score for the patients, which happens once every 3 months. And the task two is to predict the patient self-assessment scores, which happens more frequently, I think roughly 1 month. So we wanted to see if we can combine the task 2 data to task 1 so as to somewhat triple the data that we have. Now, on the graphs on the right side, you can see the blue dots are the scores that are assigned by the clinician, and the orange ones are the ones that are self-assigned. And we can see that they basically follow a pattern. So one thing to note is that whether or not they are in agreement with each other, which means whether or not we can use them in a combined way. So as we can see, the top graph shows a pretty good progression. And fortunately, most of our patient questions follow this pattern. So we are able to use them to achieve more data. And the second advantage of this is the second graph, where we had a single clinician assigned score, I think, the single blue dot. And so this basically means that we would have had to discard this patient for our training, because in our training, we use our test is such that we are given a particular day's ALS scores, and then we are given a number of days after which we have to predict what will be the score 10 days after the day where this score happened. And the sensor data for this period is given. So if we are given only one score for this particular patient, then we could not have used this in our modeling. So all the sensor data for this particular patient would have been useless. But with these scores added to the self-assessment scores added to the mix, we will now be able to make use of this patient data as well. As Ritesh mentioned, the data set is small, so having to throw away a patient just because it has a single score would have been non-ideal for us. Now, the third graph shows the case where we are not able to use that, because as we can see, the self-assessment is pretty much not in agreement with the clinician scores. So this particular patient, for this particular question, marked 0 on every time he had to fill the questionnaire. So, and this is as far as 4, difference of 4 on a range of 4 for the patient around what this is 40 days of from the days of diagnosis. So we will filter out these particular cases to not combine them, the data for these particular cases. Now looking at the numbers, how many of these we will not be able to use. So we tried to use chi-squared way to assess whether the distribution can be called coming from the same distribution. I mean, the two scores are coming from the same distribution or not. So out of the patient question tuple, out of 610, 51 of them we will not be able to combine. But the good news is that for the rest, we will be able to do so. So this will allow us to have more labels and should allow for better modeling. Next slide, please.
Yeah, I'll go over Alex's slide. This is the last slide. Alex is our another team member. He's not here. I mean, he's in a different time zone. Well, the same time zone as Anthony, but he's not here. So he's mentioned he's worked quite a bit on modeling as well. Primarily working on the mixed effect and random effects, fixed and random effects modeling, because as this is panel data, if you were just look at one patient data, it is almost like a time series data. You have some data at every time point. So there is a lot of value in trying to predict or use it as having a fixed effect and random effect, right? Where you have fixed effect being something that is common among all the patients, and random effects mean basically something that is particular to the patient, right? Like seasonality in sales, right? You have seasonality and then something constant. So he has done some work there as well. He did get some good results. 0.65 RMSE is what I know that he got by time series forecasting. But as Shashank mentioned, the problem was again the same. The moment we add on to some sensor data, this model just loves to overfit it immediately, and training error will go down, test will go up immediately, right? So we trying to still work through our modeling approach, and one of the other critical items is to have a very important cost validation strategy here. We want to make sure that we don't take the sequences out of one patient for validation, but we take the entire patient out and keep the patient for validation or test set, and not include any data from that patient, because otherwise there is a chance of we accidentally future looking into the data set for a given patient and then trying to predict the previous score, right? So that there is always a chance in time series data that's a problem, leaking patients' trajectory. So we're trying to create a pipeline with the cross validation in it, and yeah, that's I think at this point that's about it. And we also looking at dimensional reduction. We have overall 90 features in our data set. Although the data set is small, but we have 90 features. We want to try to see if we can reduce the dimension to smaller. We have been trying to get it to 63, but I think Alex did some other work. He was able to go down to around 20 with 95% variation captured within those 20 variables. So we're trying to see if we can make use of that as well to speed up our experiments for modeling. Yeah. So that's about it for now. And here is a quick visualization of Alex's dimensionality reduction. He's mentioned that we can last point over here on the right hand side graph. He mentioned that 20. He did a PCA, and there are 20 vectors that can contain 95% of the variations in all the features. And the top score is just a score trying to show how over a period of time the scores usually decrease, right? Because it's a neurodegenerative disease, right? Unfortunately, you would expect patients' health to kind of deteriorate over time, and that's why you would see the score go down over time, right? So that's what general trajectory. You see some of the scores do go up, but primarily it's a downtrend for all the 12 questions in the graph. Yeah, that's about it.
All right,
I'm done.
Thank
you.
Thank you, Ritesh. Thank you, Shashank. And thank you, Alex, who not here. Great. So next we'll go on to the life play presentation. So the first of which is birdclef, which I'll talk about. So birdclef is a competition that's focused on classifying bird calls. We have hours of audio. We want to be able to select the specific points where there are bird calls, and of those, what species are they? So the approach that we're going to be taking this year involves using a neural codec and a two-stage classification procedure. So a neural codec is kind of like a normal audio codec. So you might have like MP3s or AAC or OGG. These are all codecs that are able to take raw numbers that represent sound and to compress them in a format that is efficient and can be played by all sorts of different devices. It saves a significant amount of space. And so neural codecs try to capture data and compress it in a similar way. So instead of using things like the discrete cosine transform, they use transformers and lots of layers of convolutional networks to reduce the data down into a smaller space. So we're going to be using encodec to compress the data into an embedding space, and then we're building a detector which is able to figure out whether there's a bird or not, and then a classifier that may be built on a lower dimensional representation of whatever encodec spits out. So we'll have a pipeline that should be a little more complex than years before. And then I'll pass things off to Adrian, who's been doing some work in learning more about encodec. Adrian?
Yeah, can you hear me?
Yep.
Awesome. So encodec is, as Anthony said, neural audio codec, and it uses this encoder-decoder model with a quantized latent space. And the authors call this process residual vector quantization. And this is simple but powerful. As you can see in the grid on the right, the points are quantized into the closest bins. Then within each bin, you quantize again on the residual. And you keep doing this, and the number of times you quantize controls the level of compression. And this is all done without retraining the model. So that's really nice. That allows for variable bit rates. And there's also an optional language model with transformers we can turn on and off for some extra compression. Our goal is to use encodec as an initial layer of dimensionality reduction. But in addition to that, we found that it implicitly reduces some noise. On the right, we can take a listen to a bird call recording, and then there are 6 and 3 kilobit per second bitrate reconstructions from encodec. I guess, Anthony, could you play around 5 seconds of each?
Yeah, does this work? Oh, yeah. Can you hear that? No. Do I need to share the
I
audio
don't
on
think
my?
so.
Let me try sharing audio on my device. Where would this setting be? Advanced sharing? Oh, this is unfortunate. Share computer sound. I have to get my password. Maybe you should have tried this at the beginning. Oop, do I not know my password? Do you hear this now? Yeah. Okay. So that's the original. Six kilobits per second, and then 3 kilobits per second.
Yeah, so as you can hear, it's pretty good. You can hear it's even though it's 3 kilobits per second, such a low bit rate, the quality is surprising, and some of the background noise is also removed. I guess so. Our plan is to first visualize some of these embeddings with PCA, UMAP, maybe some clustering at first, and then we want to test on a small subset of data using call, no call labels. And then we want to fine tune encodec on birdclef data. So right now, this what you just heard was just pure encodec without any additional training. So we want to fine tune that on bird data. And then finally, we want to train classifier on embeddings. Maybe we'll probably have some extra layer of dimensionality reduction between. Next slide, please. And this is just a more detailed diagram of encodec. You can see the encoder followed by the quantizer and decoder. There's also this discriminator for some additional adversarial losses. And for our purposes, so the transmitter uses, like, let's say you're trying to compress some audio and give it to someone else. So the transmitter uses encoder and quantizer, and you would send that over to the receiver, and then they would use the decoder. For our purposes, we want the low dimensional embeddings, so we would be using just the encoder and the quantizer.
Great. So I believe that's everything for birdclef. Thanks, Adrian, for the in-depth overview of encodec, and it was interesting to actually hear some of the audio that came out of it. So I'm looking forward to seeing how birdclef will pan out this year. The next will be geolifeclef, which is also a project that I am leading. So in the last month, we have the data downloaded, and the goal of geolifeclef is to do species density prediction. So given a map of what I believe is Western Europe, our goal is to predict what species might exist at a particular area, given a bunch of satellite imagery and bioclimatic information, as well as some time series about the region. So for this competition, our focus is going to be on building a really good baseline. So the data that's given to us is approximately 5 million rows that contain a latitude, a longitude, and a date, and a species. And so with this data alone, I think we could build a pretty good baseline model that just using the metadata is able to have some good prediction of what species might be. And this is a good place where we can build on top of. Generally, the approach is going to be some form of representation learning, because satellite imagery and time series data is really challenging to work with. So The goal is to be able to take patches of geospatial data, whether it be an image, whether it be elevation, whether it be the category of the biome. We want to be able to take this information, convert it into a vector space that we can feed into a model. And so there are a couple of ways of doing this. The first, which is probably going to be the first approach after the baseline, is to just take a low dimensional representation of all these data points. So you can imagine you have you have millions of tiles. And you have this big matrix where one tile is represented as a row, where it might be 256 pixels by 256 pixels, but laid out into one row. And we have several million of these. We can cut that down into a smaller dimension, and then with this data, we can feed a gradient boosted decision tree to make a determination on what species might be in a particular area. We can do the same thing with neural networks. So there is a model called TileDevec, which is able to build an embedding that uses a triplet loss. So you're comparing one tile with a nearby tile and contrasting those against one that's far away. And by doing this over and over again and sampling from the map, you're able to learn a representation that can transfer downstream. So these are kind of the two major approaches that I think the team will take in order to have some sort of solution on the leaderboard. This is really challenging. This is a really challenging problem because there are a lot of engineering hurdles in order to get to the end goal. For example, we're given I think it's a 11 gigabyte TIFF file. It's an image. It's a 13 gigabyte image. And we need a way to process the image so that we can process it in a data parallel way. So there's lots of things to kind of handle here. So that is geolifeclef. We're building the baseline. We'll probably make the first submission in the next few weeks, and then we'll be able to get into the more interesting representation modeling. For the next presentation, we have plantclef, and for plantclef, I'll hand things over to Amrilla.
Hey, hi everybody. So for plantclef, just as a little recap of everything that we have been doing so far and also the problem. So plantclef is a multi-label classification for images, and data was only available actually this Monday, March 11th. And the dataset contains almost 8,000 species of plants and a little bit over than 1 million images, which is about 280 gigabytes of data, which is quite a lot. So the organizers also made available some metadata that we can use, as well as a pre-trained, fine-tuned vision transformer model, the Dino V2, that was developed by Meta. And the main challenges that we're trying to solve is that the test data, it's really different than the training data. So the test data has multi-label images, and the training data has only single label images, so one plant species per image. And we're going to be trying to tackle that problem I'll be going over through that in the next slides. So next one. So, okay, so going over very quickly and briefly about the solutions, the proposed solutions that we have. The first one is a transfer learning using self-supervised foundational vision transformer, which basically we're just going to be using the model, getting the embeddings from the images, and then training a classifier on the embeddings and making the classifications on that. We're also going to be doing a different approach that is more innovative, as we can say. So we're going to be transforming the multi-label classification problem into a ranking problem. So instead of directly predicting the labels, we're actually going to rank the likelihood of a species belonging in the image. So yeah, those are the two approaches that we're going to be doing. Next one, Anthony. Okay, so because the data set was only made available this week, we haven't been able to do a lot of modeling yet. So I just want to kind of highlight the main challenges that we are facing right now, since it's such a huge data set. So it took 11 hours to download and extract the data set locally on the VM, which is quite a lot. The first time I tried to do, I faced an issue with the VM being preempted, as a lot of you guys are aware of it. So that was a huge challenge. Another one is just creating and writing the image to Parquet pipeline that we have, which we are getting the images, converting them to binary, creating a PySpark data set, joining that with the metadata file, and then writing that to GCS. That's an entire pipeline. And because the data set is so huge, you're gonna have to account for a lot of memory issues that are gonna happen. And also after that, creating a multi-label training data set that basically entails that since our training data is single label, but our test data is multi-label, we actually want to concatenate the images together to create a multi-label data set so we can use for training. But that also has a lot of issues, because not every plant species, we cannot just randomize creating this concatenation of images randomly, because not every single plant species it's close to each other based on the region. So one plant species might be on this region in Europe, and another plant species might be in a completely different region where they don't belong together. So we're gonna have to do a lot of data engineering to actually get the plant species that are near each other, so we can build this data set correctly, so we can train on that. And just regarding solutions for the infrastructure part of it, we're going to be trying to use more instances where they're not preemptible regarding building the pipeline, and also doing some optimization things like number of tasks and partitioning the sizes of the Spark clusters. So yeah, that's what we've been doing so far, and we are very much looking forward to actually getting to the modeling phase.
Great. Thank you, Murillo. Next, we have a quick update from snakeclef. snakeclef is another life play competition that's focused on classifying different snake species based on classifying different snake species. And it's interesting because lots of snake species have evolved in a way to have coloring that mimics other snake species. So there are poisonous snakes that have very colorful coloring, and there are non-poisonous species of snakes that also have the same coloring. So it can be a challenge to identify these snake species. So what we've gotten so far is kind of an approach for a baseline for this challenge. And so we have embeddings from Dino V2. We're in the process of trying to run inference in a data parallel way across multiple machines. And once we get those embeddings from the Dino model, we'll learn a very simple model from it that we can use to make our initial submission to the competition. I'll be naive, but we'll have the pipeline kind of set out of training and deploying and getting to know how to use the Hugging Face platform. I believe it's Hugging Face. The second is once we have this baseline model down, we'll go into more sophisticated modeling approaches. So I think the very first thing to maybe try is to see what it's like to fine-tune Dino V2. I believe this is computationally expensive, so it may not be a viable approach. But this is the same thing that the plantclef organizers have done. They've fine-tuned a VIT model for the domain of plant species, and we can probably do a very similar thing for snake species. The second thing that I think would be interesting is to take the output of the VIT of Dino V2. It's a fairly big vector space that we get out of it. We have basically a token that's a small patch of the image, and we have many of these. So what we could do is build another layer that does dimensionality reduction of that output, at the same time utilizing the custom metric that's being used for the snakeclef competition. So this is what we have for the snakeclef competition. Next, we have fungiclef, which is very similar to snakeclef, and I'll be also presenting this. Credits to Chris for building out the slides. So fungiclef, very similar to snakeclef, except instead of snakes, we have fungus. And fungus or fungi are also, they can also be very poisonous. So by using images of fungi, we want to be able to determine what species they are and whether they're poisonous or not. So the competition is now live on Hugging Face. There are some changes from the last year in terms of how the competition is run. So there's no more limitation on the model size. I think last year the models were asked to be under 1 GB of GPU memory, and the reasoning behind that is because it'd be useful to deploy these on phones. But that size limit is now removed. It just needs to run on a single, I believe it's a 4 vCPU instance with a T4, which has 16 gigs of VRAM and 15 gigs of RAM. So we could put a pretty sizable VIT model on this instance. It's using the same loss function as last year, which puts emphasis on false. It puts emphasis on classifying poisonous species wrong, which is interesting. Yeah, there's extra data is not allowed in these competitions. It generally isn't allowed. So you're not allowed to use private data sets for a lot of competitions. You're not allowed to use external data sets for a lot of competitions. And so this is one of those. So the strategy is, again, likely to be a Dino V2 based model, probably taking sharing a lot of knowledge across plantclef and snakeclef and fungiclef. There's a lot of metadata in the fungiclef competition, which means that we can incorporate aspects of language models into multimodal models into this competition. Again, like snakeclef, it'd be useful to have kind of this custom loss function that's applied as a dimensionality reduction kind of stage, as well as maybe learning that lower dimension space through a contrastive approach. So there are a couple open questions. One is that this competition has an unknown class. So there are a lot of species that aren't actually known, and how to include unknown species into the competition or into the modeling is still kind of unknown. There's a couple of approaches that are written down in the slides. We're also trying to figure out what might be the best way to include all the metadata into the training. And so that might include a language model, that might include ways of trying to figure out the importance of the language model embeddings with the vision embeddings, maybe using a multimodal model. And there's still kind of an open question is like, how much of the work can we reuse across the teams? So those are all things that still need to be handled. So that is all for LifeClay. And next, I'd like to hand things over to Ben for Pan and Touche.
All right, thanks, Anthony. So for those of you who may not remember, Pan is the competition where we're trying to detect AI written text. And the competition is fairly new this year. They haven't offered it in previous years, and they've just released a very small data set. And the competition committees really encourage the collection of outside data. So we've collected, a few gigabytes of text written from various LLMs and found on like Hugging Face and like, intro to Wikipedia, just various arrays of literature from different genres. Our team is comprised of about 3 people, and our approach is to kind of take 3 separate approaches and maybe run some kind of ablation study on some sort of ensemble and running them individually. So in the next few slides, I'll kind of detail our approaches, but they revolve around a entity graph neural network approach, a fine-tuned Roberta approach, and another graph, but this time instead of entities, it's more focused on like the dependency graph of a text. So on the next slide, I think we have the entity graph approach. So that picture didn't come out as well as I thought it would, but it's kind of detailing like the factual coherence of a text. This is my approach. It's focusing on like I said, the factual coherence of the structure of a document. So it's based off of a paper we found that I'm trying to implement into our solution. But how it works, and we're very close to getting this into production, but how it works is we take a document. In our case, they're typically shorter, around 500 words or so. We'll tokenize the document into several sentences, and we'll calculate the next sentence prediction, which is like a pre-trained BERT model that takes sentence A and sentence B, and then tells you sentence B follows sentence A with 99% coherence or something like that. We take the classification token layer from a pre-trained Roberta model as kind of like the semantic essence of a document. And then we take from our tokenized sentences, we run a named entity recognition model on each sentence. So we'll have, for instance, in the sentence, the quick brown fox jumps over the lazy dog, fox jumps dog would all be entities. And so we end up kind of creating this like list of lists of each entity for each sentence. And the approach is to draw a graph effectively. So we'll create inner sentence edges between all the entities in a sentence. And then we also want to draw sentence edges between sentences. So to do that, we'll kind of iterate through all the entities in our sentence and run like a cosine similarity on each entity pair. And if it's above a certain threshold, we say, all right, draw the edge. To get the similarities, what we're doing is once we have our sort of list of entities in a sentence, in a document, we will take those entities, turn them into Roberta embeddings. Some entities will be 3 words, some will be 1 word. So we end up kind of averaging the 3 words so that they're all 1 by 786 vectors. We also then take those entities, we'll go grab the vector from a Wikipedia 2-back embedding. So we kind of have this Roberta embedding and this sort of factual representation that you get from Wikipedia, concatenate those, and then we'll pass those. So once we have that, we kind of have this like adjacency matrix of each entity in a document and an edge between each entity, obviously. Once we have that, we'll kind of run that through a graph neural network where we'll run it through a variable number of graph convolutions. And if you don't know what a convolution, it's sort of like in an image, you kind of span the image into sort of blocks. It kind of does the same thing for nodes in a graph. And once you've run it through these convolutions several times, you kind of have these graph enhanced representations of each node. So once we do that, we will go and then pass through our list of lists in our document that kind of reads, all right, in sentence 1, we have entities 1, 2, 3. In sentence 2, we have entities 3, 4, 5. So et cetera, et cetera. We'll go and we'll look up the index to that entity into the adjacency matrix. Then we'll average them across each sentence so that each document, if it has, say, 7 sentences, each sentence will kind of have like an average node representation of all the entities in it. We'll then run that through an LSTM and kind of create this sort of temporal element to understanding like the sequence of the sentences. We go back, we grab the next sentence prediction that kind of multiplies, so we'll have like the entity recognition for sentence 0 and sentence 1, and we also have the next sentence prediction for sentence 0-1 pair, and so we'll multiply each next sentence prediction by sentence A and B for their representations. We'll kind of add all that up into the final like graph enhanced LSTM representation, concatenate that with the classification token, and then run that through a classification layer. And that's how we're kind of getting our factual coherence part of the solution. So on the next slide, I think we have the fine-tuned Roberta approach. So what we're doing here is we have like a Roberta for classification model. We then take a LoRa. It's like I think this is Abhinav's approach. I don't know if he's on, but he takes a LoRa to compress the amount of trainable weights
I
in
can
a.
talk about it.
Oh, you're here. Okay, Abhinav, you want to take the lead? Go ahead. I didn't realize you're here. Sorry.
Sure. So Roberta, the LoRa method, what it does is that it looks at the Roberta model and it decomposes the weight matrices inside the model into two low rank matrices. So the rank of that matrix, like here A and B, is like something of a hyperparameter that needs to be tuned. But so it decomposes all the weight matrices into these matrices and drastically reduces the number of trainable parameters for the model. So the method that we were looking at, we were able to get around 0.5% of the trainable parameters compared to the original model for fine tuning. So using that approach, we are using the Roberta classification model, passing it through LoRa to reduce the number of trainable weights, and then finally fine-tuning on our data set for predicting whether it's a human text or an AI written text. Ben?
Thanks, Abhinav. Yeah, thank you. So our last approach is by Jack. I know he's not on. His approach is very similar to mine in that instead of taking the entities of a document, he's building a dependency graph from each word. So for example, you can see I prefer the morning flight to Denver. Each kind of word has, if you can think of it as a graph, has like a edge to each word, right? And what he's doing is he's creating a edge feature graph where he'll sort of try to take into consideration the relationship each word has to each other. And I think on the next slide, he kind of details more into it. So he converts the sentences into dependency graphs with spaCy. Similar to what I do, he takes the Wikipedia 2 vec embeddings. He's currently trying to do like a node position, sentence position and document word position, because he's trying to find some way to model out the morning flight through Denver has, is later in the sentence versus early in the sentence. He's also trying to, again, create edges and edge weights between the relationship between each word. And he's also, when we met last night, he's trying to build a kind of, because this is a very sentence level approach, he's trying to build a way to model the dependency between sentences. So right now he kind of is looking at like a root word and trying to draw a connection between each sentence via this root word from sentence to sentence to sentence. You create a graph data set where, if you don't know, PyTorch geometrics, so really good framework for that. You basically create like this edge index and run it through this graph convolutional neural network like he's doing. It's a very similar approach to the first slide, but again, on a more of a word level versus entity level. So I think that's it for Pan. And so finally, touche. So just this one slide. Touche is a competition that's been around for a little bit. This is like its third or fourth year in the running. They've changed it slightly from prior years. In past years, you used to have to return the top 10 pictures that are relevant, but you also had to identify argumentative images, the stance of the images, and relevant images. This year, you're only doing relevant images, but they've also changed the data set slightly. So this year, they're giving us about 6,000 images, whereas in the years past, there was like 50,000. They provided some new data sets where they'll give us the image, the text from the image, the text from the web page, and they've added this year, like, I guess, I don't know what multimodal LLM they're running it through, but they'll create like these image descriptions for each image. And so what the competition is they'll give you like a list of arguments with a premise, and they want you to go find images that either support or are against. They tell you which to do for each argument. And so they just released this data set, and because it's kind of large, you kind of need a lot of scaling and a lot of computational resources. We've been kind of playing around with sort of toy data sets on previous years. And so they just released a data set, so we haven't really been able to do too much modeling. But our approach right now that we're thinking is to kind of take each of the modalities of the image, so the image description, the text, the image itself, run these through some sort of clip-based models to kind of create this lower embedding space. We also want to take the arguments themselves, project them somehow into a similar space, and train this sort of attention contrastive network where we can kind of learn this sort of self-supervised representation of each image, because the biggest issue with this is that we don't actually know what images belong to which argument. There's no label associated with any of them. So we're trying to kick around ideas. Anthony actually shared a really good article about this like guy who indexed all his iCloud photos with lava and PyGVector, and that's a very good solution that we might end up going with. But right now, I think we're trying to do the contrastive loss representation, feed that into kind of create that as like this sort of encoder where we take all the information about the image, project all 6,000 or so into this representation space, find a way to take these arguments to then query this database, return the top K samples, and then use some sort of re-ranking solution to kind of figure out the top 10, 20, whether that's maybe finding a way to use like some sort of lava or multimodal LLM that can kind of more easily understand the image, but to do it in a way that we're not running 6,000 images through this thing, asking it 100 different questions for each 6,000 images. So that's where we're at. And I think that's the last slide for me.
Cool. Thank you, Ben.
Thank you.
Some very interesting approaches for sure. For our next presentation, we have erisk, and for erisk, I'd like to have David take us through this.
Hello, everyone. So as we recall, erisk is pertaining identifying symptoms of depression. So my goal is to have a base model delivered or a solution rather. So what I'm doing is I'm extracting the keywords related to the sentences from the depression symptoms questionnaire, and then I will compare those symptoms using a pre-trained BERT model, and I will extract the top 10 results from the calculated embeddings using cosine similarity. I had some issues with dealing with the dataset, so right now I'm trying to rather reduce the search space. You can move to the next. I'm reducing the search space by filtering out the sentences that do not contain the keywords. And as I already mentioned, we're using comparison with cosine similarity. Yeah, that's for task one. I don't really have any other updates. That's it.
Cool. Thank you, David.
You're welcome.
Next, we have longeval, and I think this is the last lab. So Joshua?
Last but not least, super excited to do this project. It's me and Luis. Luis couldn't be here today. He is at work, but I'm here. So essentially, long eval, we're essentially evaluating systems for their temporal. Let me turn my camera on. Yeah, so we're essentially evaluating systems for their temporal persistence. So this project has two different tasks. The first one is a temporally persistent information retrieval system, and the second one is a more machine learning focused temporally persistent sentiment analysis binary classifier model. So for task one, our one and really only approach at this point is to use Elasticsearch and Python to parse and parse, index, analyze, and then query these documents based on the keywords that were passed. And then for the second one, we are for the binary classification model. Our three current approaches right now are XGBoost, a naive Bayes model, and a linear support vector classifier. Go to the next slide, please. So for this, for the information retrieval system, there are 4 parts of the system: parse, index, analyze, and then search documents. Currently, we have we're just using Elasticsearch as kind of our search engine, and we're kind of proving that we can use Elasticsearch to search documents that are relevant to our keyword based on how we parsed it. Currently, we can move to the next one now. So currently, this Bayes system has performed poorly for the temporally distant queries, meaning the queries that are based on documents that are a bit farther in the future. So we are investigating using text embeddings in this system and figuring out how we can potentially maybe vectorize or use text embeddings to kind of and then pass that to Elasticsearch by way of queries. So yeah, right now we do have a baseline model though. We were able to get Elasticsearch to work. It was very fun when we realized that. It was great. Very happy. Now on to the binary classification. Again, 4 parts of the model: collect the data, prepare the data, identify the data, and then classify the data. And then we get our results. So this one's a bit more involved as far as the approaches. We started out with a naive Bayes model, which was suggested by Anthony, which as till now is our best performing model, which is very funny. Essentially, based naive Bayes model just applies the Bayes theorem with a naive assumption of no relationship between the different features. We use count vectorizer and TF-IDF with this model, and we came to the conclusion that TF-IDF leads to a slight increase in model performance. For approach one was XGBoost, which is simply a gradient boost ensemble learning model. Everyone uses it. We all learned it in AI. along with gradient boost and auto boosting. To use this one, we have to convert data into the matrix object. For vectorization, we use the basic count vectorizer. We're looking at potentially applying TF IDF to XGBoost. Currently, it's performing worse than naive Bayes, and we hypothesized that it would perform better. So right now, we think that the model might be underfitted to the data. So we're working on diagnosing underfitting and overfitting with the learning curve. And for our last but not least model, we used a linear support vector machine vector classifier model, which basically performs classification by finding the hyperplane that differentiates between the classes. Differential classes plotted in n-dimensional space. It does this by transforming the data and essentially using different kernels. The kernel that we used was linear, since, hey, we have a binary classification problem. We only have these two, so let's just use linear one. So here again, we vectorized the data using both count vectorize and TF-IDF. So we have two different models trained with these two vectorizations, and came away with thinking that TF-IDF comes with the better performance. What's interesting is they count vectorize and TF-IDF seem to be opposites, if I'm understanding them correctly. Essentially, count vectorization. That's how I came to the conclusion. But it's interesting though, because you would think for a task like this that the relevant documents would all have the same popular words. Right? You wouldn't think that TF-IDF, which more so focus on rare words, would be able to would point to relevant documents, or would be able to group documents together well. I mean, tweets together well. So LSVC actually performed pretty poorly on F1 and on the accuracy calculations. Again, we think it might be underfit, and we are diagnosing it with a learning curve using loss. We're currently trying to figure out what is the correct error, if it's a mean squared error, or something else would be appropriate for these models. Further approaches, we're working on trying to slap a neural network on it. Training has been slow, so that's not working out. We're also thinking about using an LLM, a pre-trained LLM. But we really think that XGBoost and LSVC are tremendously underfit, and that's why they're performing incorrectly. So we're gonna take some time and try to diagnose diagnose our issues using that loss curve based on the amount of samples being trained. Yeah, that's what we have.
Cool. Thank you very much, Joshua. I actually have some comments, but I'll drop them in the chat for longeval. Yeah, great stuff. Like, great to see Elasticsearch running. Great to see having some solutions down for the sentiment analysis. So yeah, this wraps up the updates for all the teams. So we're coming in here at 1 hour and 15 minutes. So it does take quite a bit to get through 11 teams. So our next meeting is scheduled for, again, the second Thursday of the month. So April 11th. And so the focus of this meeting will be on kind of experimental results and maybe some of the initial working notes. But at this point, the goal is to have that first submission, maybe have a couple of variations of models that you want to try out, maybe some ablation studies, at least written down on paper, so that you don't have to suffer during that last week when the notes are due. And we ran a poll earlier before this meeting started, and we will be having another meeting in May. So it'll be the second Thursday of May, which is going to be after the semester ends. And this will be kind of the last meeting after the competitions close, before the working notes are due. And so this will be a good time to wrap up everything. So that's it. Any questions, thoughts? Cool. So let's wrap this up right on time. So let me stop this recording.